The night sky is a beautiful and permanent lie. Our galaxy is on a collision course with its nearest neighbor, Andromeda, in a violent merger that will reshape our entire corner of the cosmos. By the end of this journey, you will understand the fate of our solar system and witness the breathtaking celestial spectacle that awaits. We will unravel how astronomers know this future is certain and explore what happens when two titans of stars and dark matter slowly tear each other apart. What does it mean for our place in the universe when even the galaxy is not forever? 2.5 million light-years apart, these galactic giants have spent most of the universe's history in a slow, silent dance. On one side, our home, the Milky Way. You know its nighttime signature as that pale, milky band arching across the sky, but from a cosmic vantage point, it's a stunning barred spiral. Picture a brilliant, dense core of ancient stars, a bustling central bulge. Streaming out from that center are vast, graceful spiral arms, like celestial pinwheels, each one a stellar nursery and stellar graveyard filled with gas, dust, and billions of stars. Our own sun resides in a quieter suburb, one of the arms, orbiting that galactic center once every 250 million years. And enveloping this entire luminous structure is an immense, invisible sphere of dark matter, a gravitational anchor holding everything together. Its partner in this destined collision is the Andromeda Galaxy, also known as Messier 31. To the naked eye on a clear, dark night, it's just a faint, fuzzy smudge. But that smudge is the most distant object you can see without a telescope, a preview of our own galaxy's appearance from afar. Andromeda is the big sister in this pairing, larger and more massive than the Milky Way, with 1 trillion stars to our few hundred billion. It too is a majestic spiral, though studies suggest its structure may be more complex and disturbed, perhaps from past mergers with smaller galaxies. This idea of galaxies as separate island universes was one of astronomy's greatest revelations, championed by Edwin Hubble in the 1920s. By measuring the distance to Andromeda, he proved it was far beyond the confines of our own galaxy, a distinct city of stars in its own right. What makes their stories so compelling isn't just their separate beauty, but their inevitable connection. That vast gulf of 2.5 million light-years is not a permanent barrier, it's a countdown. For eons, the mutual gravitational pull between these two titans has been drawing them together, a cosmic attraction that has already sealed their fate. To understand the violent collision that awaits, we must first appreciate the scale and nature of the players involved. We are not just watching from a distance, we are residents of one of these island cities, and our entire local neighborhood is about to be remade. But the stars we see are merely actors on a stage, following a script written by an unseen director. The true driver of this cosmic merger, the immense gravitational hand that has already locked our galaxy and Andromeda in their fatal embrace, is something we cannot see at all. It is dark matter. To grasp its overwhelming influence, picture an iceberg floating in a dark sea. The glittering spiral of the Milky Way, with all its hundreds of billions of stars, is just the luminous tip visible above the waterline. Beneath the surface, extending 10 times farther in all directions, lies a colossal, invisible sphere of dark matter. This is the galaxy's true form, its hidden architecture. The gravity from this immense halo is what dictates the motion of everything within it, from the outermost lonely stars to the grand dance of entire galaxies. This understanding came into focus thanks to the meticulous work of astronomers like Vera Rubin. In the 1970s, she studied the rotation of galaxies, measuring how fast stars orbited at different distances from the galactic center. According to the laws of gravity and the visible mass of stars and gas, Stars on the outer edges should move slower, like planets in our solar system. But Rubin found something astonishing. They did not slow down. Stars far from the bright center were whipping around just as fast as those near it. The only plausible explanation was the presence of a huge amount of unseen matter, a dark gravitational glue holding these fast-moving stars in place. Her work provided some of the strongest early evidence that what we see is only a tiny fraction of what is truly there. This hidden mass shapes everything. When astronomers run supercomputer simulations to predict the future collision of the Milky Way and Andromeda, they are not just simulating two disks of stars. They are simulating the violent interplay of two of these immense dark matter halos, each one a ghostly sphere of influence millions of light years across. The visible galaxies are like bright markers embedded within these vast, invisible clouds. As the halos begin to overlap and intertwine, their overwhelming gravity will pull the stars and gas of both galaxies into a chaotic new dance. So while we watch the night sky for signs of change, the real story, the framework for the coming violence, is being written in the dark. The first clue to this cosmic destiny was not found in a grand telescope image, but in a subtle shift of color. For much of human history, the Andromeda galaxy was considered a static nebula, a permanent fixture in our sky. The idea that entire galaxies could move through space, that the cosmos itself was dynamic and evolving, was still taking shape. Then, in 1912, an astronomer named Vesto Slipher pointed a spectrograph at that faint, fuzzy smudge. A spectrograph is a remarkable tool that acts like a cosmic fingerprint scanner. It takes the gathered light from a distant object and spreads it out into a full rainbow spectrum. Embedded within that spectrum are dark lines, specific gaps where elements in the star's atmosphere have absorbed particular colors of light. Slipher's meticulous work revealed something astonishing about Andromeda's spectral lines. They were not where they should have been, they were shifted. When a light source moves toward you, the waves of light get compressed, like the sound of an approaching ambulance siren rising in pitch. This compression shifts the entire spectrum, including those dark absorption lines, toward the blue end of the rainbow. This is called a blue shift, and that is precisely what Slipher measured. Andromeda's light was blue shifted. It was the first concrete measurement proving that this great spiral was not standing still, but was racing directly toward our own Milky Way at a staggering velocity. At the time, the full implication was not yet understood, but that single observation planted the seed for our modern understanding of galactic collisions. Today, with instruments like the Hubble Space Telescope, we can measure this motion with incredible precision. We now know Andromeda is approaching at about 250,000 miles per hour. But the story is more complex than a simple head-on crash. Think of it like watching a car approach from a distance. You need to know not just how fast it's coming toward you, but also how much it's moving sideways. A car aimed directly at you is a very different scenario than one that will sideswipe you as it passes. Astronomers faced a similar puzzle with Andromeda. They had the blue shift, the speed toward us, but to predict the true nature of the collision, they needed to measure its sideways motion, a much more difficult task because it requires tracking extremely tiny movements across the sky over many years. It is like trying to measure the width of a human hair from a mile away. By painstakingly comparing Hubble images taken years apart, scientists finally pinned it down. They discovered that while Andromeda's sideways motion is small, it is enough to guarantee that the first close pass will be more of a glancing blow than a direct bullseye. This foundational measurement, from Slipher's first blue shift to Hubble's pinpoint tracking, transformed our galaxy from a lonely island into one half of a destined pair, locked in a gravitational waltz that has already begun. That faint blue shift is the first note in a symphony of motion written by gravity itself. To truly grasp the coming collision, we must step back and see the galaxies not as frozen portraits, but as dynamic partners in a slow cosmic waltz. Their movement follows the same universal rules that govern a planet orbiting a star or two ice skaters on a rink. Picture those two skaters starting far apart. They begin to circle one another, their paths curving as each feels the subtle pull of the other's presence. There is no track guiding them, no hand pushing them together, only the invisible, mutual attraction of gravity. With each pass, they draw a little closer, their circles tightening until finally they come together. This is the essence of our galactic dance with Andromeda. The profound insight that unlocked this understanding came from Isaac Newton centuries ago. His law of universal gravitation stated that every object in the universe attracts every other object with a force proportional to their masses. The Milky Way and Andromeda, as the two most massive members of our local neighborhood, exert an immense gravitational pull on each other. But there is a crucial difference between the ice rink and the void of space. In space, there is no friction, no air resistance to slow them down, no surface to create drag. Once set in motion by gravity, they will continue on their curved paths indefinitely, their energy conserved, spiraling closer with every graceful loop. This changes our perspective of the collision entirely. It is not a sudden, chaotic crash, but a carefully choreographed merger dictated by orbital mechanics. The timeline and the very nature of the first encounter are set by this gravitational choreography. Their approach is not a straight line, but a curved trajectory. They will swing past each other in a dramatic, glancing blow before gravity pulls them back for a second, closer pass, beginning a billion-year-long dance of merger. This dance is also influenced by the wider stage they perform on, known as the local group. This is our small galactic family, dominated by the Milky Way, Andromeda, and the smaller Triangulum galaxy, along with dozens of tiny dwarf galaxies. The combined gravitational pull of all this mass, this local cosmic neighborhood, acts as a gentle brake on any attempt to escape. It ensures that the paths of our two giants are bound together, their fate sealed within the group. Later, Einstein's theory of general relativity would refine our understanding, describing gravity not as a force, but as the curvature of spacetime itself by mass. Picture a stretched rubber sheet. Placing two heavy bowling balls on that sheet creates deep wells. If you set them in motion, they will naturally roll toward each other, spiraling into the shared valley their masses have created. This elegant framework confirms the inevitability of the merger. So while the spectacle is billions of years away, the script is being written now in the silent, relentless geometry of their orbits. Every moment brings them one step closer to their final, violent embrace. But a blue shift alone cannot tell you if you are in the path of a train or merely watching it speed past the station. To know our true fate, astronomers needed to answer a deceptively simple question. Was Andromeda coming straight for us, or would it sail by in a near miss? The answer lay in measuring its sideways drift across the sky, a tiny motion called proper motion. For decades, this measurement remained just out of reach, the uncertainty too great. Then, in 2012, a team of scientists used NASA's Hubble Space Telescope to perform one of the most precise acts of cosmic measurement in history. Their target was not the galaxy's fuzzy glow, but specific stars within it. They selected a special class of stars called Cepheid variables, whose predictable pulsations make them perfect cosmic mile markers. Over the course of 5 to 7 years, the Hubble team repeatedly pointed the telescope at these stellar beacons in Andromeda. Their goal was to detect the slightest shift in the stars' positions against the more distant, fixed backdrop of the universe. The challenge was monumental. It is the astronomical equivalent of measuring the width of a single human hair from a distance of 1 mile. Any instrument less stable and precise than Hubble would have failed. The team's lead astronomer described the process as an exercise in extreme patience and meticulous calibration, eliminating every possible source of error, from the telescope's own minute vibrations to the subtle distortions of Earth's atmosphere. When the data was finally processed, the result was clear and definitive. Andromeda's sideways motion was almost negligible. It was not on a bypass trajectory. It was aimed with astonishing precision directly at the heart of our Milky Way. That single, minuscule measurement transformed everything. It turned a theoretical possibility, a maybe, into a concrete cosmic forecast. The head-on collision was no longer just a likely scenario based on gravitational math. It was a measured fact, an event written into the future with observational certainty. The two greatest spiral galaxies in our sky are on a direct course to become one. 250,000 miles per hour sounds impossibly fast, yet this race toward collision unfolds on a timescale that defies human imagination. To grasp it, we must shrink the entire 13.8 billion-year history of the universe down to a single calendar year. The Big Bang happens at the stroke of midnight on January 1st. Our solar system forms in early September, dinosaurs appear in late December, and the entire span of human civilization occupies the last few seconds before midnight on December 31st. In this compressed cosmic year, the entire merger of the Milky Way and Andromeda from first approach to final union will take less than 1 minute. This is the scale we are dealing with, a countdown measured in billions of years, where the next major milestone is so far in the future it feels like a different universe entirely. So let us map out that minute, phase by phase, and witness the slow-motion violence that awaits. The first act, the approach, has already been underway for billions of years and will continue for roughly the next 4 billion. During this time, from our vantage point on Earth, Andromeda will grow gradually brighter and larger in our night sky. It will transform from a faint, fuzzy patch into a distinct, glowing oval. But the true drama begins with the first close pass, expected around 4 billion years from now. This is not a direct collision of the galactic cores, but a spectacular, gravitationally disruptive sideswipe. As the galaxies swing past each other, their immense gravitational tides will begin to tear them apart. Long, streaming arcs of stars, gas, and dust will be pulled out into space, creating brilliant bridges and tails of light stretching across the heavens. The familiar spiral structures of both galaxies will be utterly shredded, their beautiful symmetry lost to chaos. Consider what the sky might look like from a world orbiting a star at that time. The Milky Way band we know would be gone, replaced by a dazzling, tangled web of stellar streams. Andromeda would dominate the night, not as a smudge, but as a colossal, distorted wreck of its former self, its core glowing brilliantly amid the debris. After this first pass, gravity will not let them escape. They will swing back around, drawn together for a second, even closer encounter, and then a third. With each successive pass over the next 1 to 2 billion years, they will lose more and more of their individual identities, their stars becoming increasingly mixed in a growing, chaotic cloud. The final merger into a single, new galaxy will likely be complete around 6 billion years from now. What becomes of our solar system through all this? The distances between stars are so vast that direct stellar collisions are incredibly rare. Our Sun and its planets will almost certainly survive the gravitational turmoil physically intact, but we will be thrown onto a new, wild orbit within the emerging galactic hybrid. We will become citizens of a galaxy that no longer resembles either of its parents. This new entity, often called Milkdromeda or Milkdromeda, will likely take the form of a giant elliptical galaxy, a vast, football-shaped swarm of stars with little of the gas and dust needed to form new stars. It will be a quieter, redder, and older galaxy, the product of a violent merger that marked the end of an era for spiral giants in our local group. To witness such a transformation would be to watch the fundamental architecture of our home in the universe be rewritten, a reminder that even the grandest structures are temporary in the flow of cosmic time. 4 billion years from now, the night sky will become unrecognizable. The familiar, misty band of the Milky Way, our galaxy's serene backbone, will be gone. In its place, a colossal, distorted disk of light will dominate the heavens, its core a brilliant, hazy jewel. This is the Andromeda Galaxy, no longer a distant smudge but an immense structure spanning a quarter of the sky, its spiral arms now visibly warped and stretched by an invisible hand. That hand is gravity, and it is beginning the slow, violent work of tearing two galaxies apart. This first close pass is not a head-on crash, but a gravitational sideswipe of staggering scale. As the cores of the Milky Way and Andromeda swing by each other, their mutual pull creates immense tidal forces. Think of the ocean's tides on Earth, where the moon's gravity stretches the planet's water, creating a bulge. Now magnify that concept to a galactic scale. The gravitational pull from Andromeda will stretch our galaxy, and ours will stretch Andromeda in return, but they are not solid bodies. They are vast collections of stars, gas, and dust, each loosely bound by gravity. The side of our galaxy facing Andromeda will feel a stronger pull than the side facing away. This difference, this tidal force, is what begins the spectacular destruction. The most beautiful consequence of this violence is the birth of tidal tails. These are long, graceful streams of stars and gas, pulled out from the main bodies of both galaxies like cosmic taffy. In supercomputer simulations of the event, we see these majestic arcs of light emerging, brilliant bridges of stolen material connecting the two giants as they pass. From a hypothetical future Earth, the sky would be crisscrossed with these luminous rivers of stars, a celestial tapestry of creation born from destruction. But the drama does not end with rearranging old stars. The same forces that pull gas clouds into these streams also compress them. When vast clouds of interstellar hydrogen are squeezed by the galactic tides, they collapse under their own gravity, igniting a fireworks display of star formation on a scale unseen in either galaxy for billions of years. Bursts of brilliant blue-white stars, massive and hot, will light up the tidal tails and the distorted spiral arms. The galaxies will not just be torn apart, they will be set ablaze with new light, a final, furious burst of stellar birth before the long merger into an older, quieter form. This first pass is merely the opening act. The galaxies will not coalesce here, they will swing apart again, forever changed. Their elegant spiral structures, forged over eons, will be irrevocably shredded. They will become two mangled wrecks of their former selves, locked in a gravitational dance that guarantees they will return. The sky will never be simple again, a permanent testament to the fact that even the grandest islands in the cosmic sea are not immutable. They are fluid, dynamic, and subject to forces that can, in a single celestial moment, rewrite their entire story. The shredded spirals and brilliant tidal tails are a spectacle for the ages, but they raise a deeply personal question for any future consciousness looking up from Earth. What becomes of our Sun, and by extension our solar system, in this galactic demolition derby? The answer is both reassuring and astonishing. In the vast emptiness of a galaxy, stars are incredibly far apart. If our Sun were the size of a grapefruit, the nearest star would be another grapefruit over 2,000 miles away. This immense spacing means that even when two galaxies containing hundreds of billions of stars slam together, direct collisions between individual stars are almost unheard of. The solar system will not be smashed by an incoming sun. The real danger is not collision but harassment. This is the era of gravitational chaos, where the smooth orbital paths of billions of stars are violently rewritten. As the galaxies intertwine, every star feels the shifting pull of not just one galactic core, but two, plus the immense, invisible halos of dark matter, and the countless other stars being tossed about. It is a cosmic game of pinball on the grandest scale imaginable. Stars can be slung into wildly new orbits, hurled from the inner regions to the outer halo, or even ejected entirely into the dark intergalactic void as rogue stars, destined to wander alone forever. So where does our solar system land in this chaotic redistribution? To find out, scientists don't just theorize, they run the experiment millions of times inside supercomputers. Projects like the IllustrisTNG simulation create virtual universes, modeling the physics of dark matter, gas, stars, and supermassive black holes to watch galaxies like our own form, evolve and collide. By creating digital clones of the Milky Way Andromeda merger and tracking the fates of star systems like ours, they can provide statistical probabilities. The consensus from this virtual forecasting is profoundly comforting. While our solar system will almost certainly be gravitationally punted from its quiet suburban orbit, it is very likely to remain bound to the new merged galaxy. The most probable outcome is that we will be flung much farther out into the extended stellar halo of the new Milkdromeda. We will exchange our familiar spiral arm for a more isolated existence in the vast, sparse outskirts of a giant elliptical galaxy. The night sky would be dramatically darker with fewer nearby stars, but the planetary system itself, the Sun, Earth, and all the planets should remain physically intact, orbiting one another as they have for billions of years. This addresses a core human concern about such an apocalyptic-sounding event. The stage upon which our solar system performs may be violently swapped, but the actors themselves, the planets and their star, are likely to survive the show. While our solar system may be flung to the galactic suburbs, the true climax of the merger unfolds in the crowded downtown core. At the heart of the Milky Way, hidden within the radio source Sagittarius, a star, lies a sleeping giant, a supermassive black hole with the mass of over 4 million suns. Andromeda harbors an even more colossal counterpart, tipping the scales at a staggering 100 million solar masses. These invisible monsters are the final and most powerful dancers in the merger ballet. For billions of years, they have lurked quietly at the centers of their respective galaxies, their immense gravity governing the orbits of nearby stars. But the galactic collision will awaken them, setting the stage for the most energetic event in our local universe since the Big Bang. As the galaxies first pass and then intertwine, their central black holes will be left behind, each still anchored to the densest cluster of stars in their own galactic core. They will not rush toward each other. Instead, they will begin a slow, inexorable sink toward the center of the new, blended galaxy. This process is driven by a fascinating phenomenon called dynamical friction. Imagine a heavy object moving through a dense crowd. As it passes, it gravitationally tugs on the people around it, creating a slight wake of denser crowd behind it. This wake, in turn, exerts a gravitational pullback on the object, slowing it down. In a galaxy, the black hole is the heavy object, and the surrounding stars are the crowd. As the black hole moves through the sea of stars, its gravity pulls stars toward it, creating a dense stellar wake behind it. The gravitational pull from that wake acts as a brake, steadily sapping the black hole's orbital energy. This causes it to spiral inward, sinking toward the lowest point in the new galaxy's gravitational well, the very center. Over hundreds of millions of years, the two black holes will each undergo this process, drawing closer to the core and inevitably to each other. Eventually, they will find themselves locked in a binary orbit, two incomprehensibly heavy partners whirling around a common point. This dance will be spectacularly violent. As they orbit at a fraction of the speed of light, they will churn the space-time around them like a cosmic blender. An astrophysicist studying such events might describe this phase as the universe's most powerful engine of chaos, warping the paths of any star that dares to venture near. But even this binary state is not the end. Their orbit is not stable. With each dizzying loop, they lose a tiny amount of energy, which is carried away in ripples across the fabric of space-time itself. These ripples are gravitational waves, a prediction of Einstein's theory that was directly confirmed only in the last decade. The emission of these waves acts as a relentless brake. The black holes orbit faster and faster, closer and closer in a final, fatal spiral. In the last few moments before merger, they will be circling each other thousands of times per second. Then, in a flash of energy that would outshine every star in the Milky Way and Andromeda combined, they will collide and become one. The resulting merger will send a final, thunderous burst of gravitational waves ringing out across the cosmos, a signature that future civilizations with the right technology could detect from billions of light years away. This event marks the final act of the galactic merger, the moment when the central engines of two great cities unite, leaving behind a single, even more supermassive black hole to preside over the quiet, aging galaxy of Milkdromeda. The final, thunderous merger of two supermassive black holes signals a profound quieting. The chaotic pinball of stars begins to settle, and from the wreckage of two majestic spirals, a new galactic form emerges. Picture two droplets of paint, one blue and one white, slowly swirled together. They don't remain as distinct swirls, but blend into a single, new shade of pale blue. This is the essence of Milkdromeda's birth. Over the course of 1 billion years following the black hole merger, the two galaxies complete their final coalescence, their stars and dark matter fully mixing to create a single new entity. The elegant, spinning disks are gone forever. In their place stands a giant elliptical galaxy, a vast, three-dimensional swarm of stars resembling a glowing, featureless football or a diffuse cloud of light. This transformation is the ultimate legacy of the collision, a permanent monument to cosmic change. But how does a chaotic merger produce such a smooth, symmetric shape? The answer lies in a process astrophysicists call violent relaxation. During the merger, stars are flung onto wildly different, chaotic orbits by the shifting gravitational tides. They slingshot past one another, their paths constantly perturbed. Over time, this gravitational scrambling acts like a cosmic mixer, randomizing the orbits of billions of stars until no preferred direction remains. The organized circular motion of a spiral disk is erased, replaced by stars moving every which way like a furious swarm of bees. This creates the smooth, rounded appearance of an elliptical galaxy. An expert might describe it as the universe's way of reaching a new equilibrium, a state of maximum stellar entropy where the energy of the collision has been evenly distributed throughout the system. The characteristics of this new galaxy are a direct testament to its violent origins. Milkdromeda will be far larger than either of its parents, a titanic collection of up to 1 trillion stars. Its stellar population will be older and redder. The furious bursts of star formation ignited during the first passes will have long since burned out, their short-lived blue giants having exploded as supernova eons ago. What remains are the longer-lived, cooler red stars, and the galaxy's remaining gas and dust will have been either used up in that final starburst or blown away by the energetic outflows from the merging black holes. This leaves Milkdromeda quiescent, a quiet, red and aging giant where new stars are rarely born. It is a galaxy entering its retirement, a serene and majestic structure whose calm exterior belies the spectacular violence of its creation. Yet within this chaos lies a breathtaking act of cosmic rebirth. The violent gravitational tides that tear the galaxies apart also perform a vital creative function, squeezing the vast clouds of interstellar gas and dust that drift between the stars. Picture these nebulae not as serene cosmic paintings, but as raw, unformed building material. As the galaxies swing past each other, these immense gas clouds are slammed together by colossal shock waves, like ocean waves crashing in a storm. This sudden, violent compression is the ultimate trigger for star birth. When a cloud of hydrogen gas is squeezed past a critical point, its own gravity takes over, causing it to collapse inward. At the heart of that collapsing cloud, pressure and temperature soar to unimaginable levels, millions of degrees. This is the moment of ignition, where the furnace of nuclear fusion lights for the first time, and a new star is born. In a normal galaxy like ours today, this process is slow and steady, a trickle of stellar formation, but during a galactic merger, it becomes a torrent. The entire event transforms the galaxies into what astronomers call starburst galaxies, where the rate of new star formation can be hundreds of times greater than in a quiet spiral. To see our future, we can look at present-day examples of merging galaxies like the famous Antennae galaxies. In telescope images, they are a tangled mess of two spirals, but within that mess are brilliant blue knots of light. Each of those knots is a superstar cluster containing the furious glow of millions of newborn stars, all ignited by the collision. Their intense blue-white light is the signature of massive, hot, and short-lived stars, the kind that only form in such prodigious numbers during these extreme events. So while the merger dismantles the old galactic structures, it simultaneously uses the wreckage to build something new on a staggering scale. This period of intense stellar genesis is the galaxy's fiery renaissance, a brilliant, beautiful counterpoint to the gravitational chaos unfolding all around it. A brilliant new sun could blaze into the night sky without warning, not as a point of light but as a searing disk. This is not science fiction, but a plausible future for many worlds during the galactic merger. As stars are flung onto chaotic new paths, close encounters between stellar systems become a real possibility. For a planet orbiting a star in this turmoil, the sky would be permanently rewritten in an instant, its familiar constellations ripped apart by the intruder's glare. While direct star-star collisions remain rare, this gravitational pinball game poses profound risks to the delicate architectures of planetary systems. The greatest danger is not collision but disruption. A star passing even a light year away, a cosmic hair's breadth, can exert a significant gravitational kick. This nudge can destabilize the carefully balanced orbits of planets, sending them spiraling into their sun, ejecting them into the frozen void, or causing catastrophic collisions within their own system. A once stable, Earth-like world in a habitable zone could find itself flung into a deep freeze or scorched into a barren rock, all because its parent star had a close gravitational encounter with a stranger. Alongside this orbital chaos comes a surge of radiation. The same starbursts that create beautiful blue star clusters also produce massive, short-lived stars that die in spectacular supernova explosions. The frequency of these cosmic detonations would increase dramatically throughout the merging galaxies. A nearby supernova within a few dozen light-years could bathe a planet in lethal levels of X-rays and cosmic rays, stripping atmospheres and irradiating surfaces. As one astrobiologist notes, life, once established, is remarkably tenacious, but these conditions present a severe test. They force us to consider the concept of a galactic habitable zone, the idea that only certain regions of a galaxy are conducive to complex life over long timescales. Traditionally, this zone is thought to be a quiet suburb, far from the radiation-dense core, but with enough heavy elements to form rocky planets. A galactic merger violently reshuffles this entire map. Quiet suburbs can become chaotic downtowns, and previously dangerous regions might settle into new tranquility. For any life forms or future civilizations witnessing the merger, their survival would depend on a cosmic lottery. Whether their solar system's new orbit lands them in a relatively placid backwater of Milkdromeda or a still-churning, radiation-filled region. It expands our view of cosmic destiny, reminding us that a planet's fate is tied not just to its star, but to the grand and sometimes violent dance of its entire galaxy. The final shape of Milkdromeda reveals a universal truth about galactic life cycles. This transformation from two elegant, star-forming spirals into one red, quiescent ellipse is not a random accident. It is a fundamental process in cosmic evolution. To visualize it, picture a meticulously structured garden with neat rows of vibrant young flowers and carefully tended pathways. This is a spiral galaxy, ordered and full of youthful activity. Now imagine a powerful storm sweeping through, churning the soil, scattering the seeds, and mixing everything together. When the storm passes, the garden is gone, replaced by a wild, beautiful meadow where plants grow in every direction with no single pattern. This meadow is an elliptical galaxy, the natural end result of a major merger. Astronomers organize this grand diversity of galaxies on a simple chart known as the Hubble sequence, often called the tuning fork diagram. On one side of the fork's handle are the featureless, round ellipticals. On the two prongs are the spiral galaxies, barred and unbarred, like our Milky Way and Andromeda. For decades, this sequence was seen as an evolutionary path, but we now understand it is more like a family tree of outcomes, where mergers are the powerful events that can push a galaxy from one branch to another. The key mechanism behind this shift is the randomization of motion. A spiral galaxy is a graceful, spinning disk. Most of its stars orbit the center in the same direction, on roughly the same plane, like cars driving on a giant celestial roundabout. This ordered rotation is what creates the thin, flat structure and the distinct spiral arms. A major merger violently disrupts this harmony. As the two galaxies intertwine, stars are pulled and slung onto wildly different paths by the chaotic gravitational tide. They are thrown into orbits that are tilted, elongated, and moving in all directions. This process, called violent relaxation, effectively scrambles the organized rotation. The result is a three-dimensional swarm where stars buzz around like bees in a hive with no preferred direction. This is the essence of an elliptical galaxy's shape. Alongside this orbital chaos, the galaxy's lifeblood is drained. Spiral galaxies are rich in the cold gas and dust needed to birth new stars. During the merger, several fates befall this material. Vast amounts are funneled toward the center, feeding the supermassive black holes and triggering those brilliant, final starbursts. Much of the remaining gas is heated to extreme temperatures by the shock waves of the collision and the radiation from all those new stars, making it too hot and energetic to collapse and form new suns. Some may even be blown entirely out of the galaxy by powerful winds. With its gas depleted or heated, the new elliptical galaxy loses its ability to create new stars in any significant numbers. Consequently, its stellar population ages uniformly. The massive, blue, short-lived stars from the Starburst era die off in just a few million years. What remains are the longer-lived, cooler, redder stars, over billions of years without fresh injections of youthful blue stars. The entire galaxy reddens and dims. This cosmic recycling, from vibrant spiral to serene ellipse, is a recurring theme across the universe. We see it in the fossil records of other galaxy clusters, where the most massive galaxies are almost always giant ellipticals, their spiral structures erased by ancient mergers. Our local group is simply following this grand, universal script, trading the graceful pinwheels of our youth for the settled, mature majesty of a combined giant. From a galaxy 100 million light-years distant, the entire drama of Milkdromeda would be a single, faint smudge of light. To alien astronomers patiently mapping their sky, our cataclysmic merger would not be a story of chaos and survival, but a data point, a single pixel in a vast survey of the evolving cosmos. Their telescopes, trained on this new patch of luminosity, would immediately detect a story written in invisible light. The first clue would be an intense flare of ultraviolet radiation. This high-energy light is the signature of massive, newborn stars, those brilliant blue giants that live fast and die young. Its sudden brightening in their data would signal the onset of the Great Starburst, the firestorm of star formation ignited when our galaxies first grazed each other. Alongside this ultraviolet beacon, their infrared sensors would pick up a powerful, complementary glow. Infrared light is emitted by warm dust, the cosmic soot heated by the light of all those new stars. The combination of strong ultraviolet and infrared emission is a textbook fingerprint of a major galaxy merger in progress, a signpost we ourselves use today to identify colliding galaxies across the universe. Their observations would grow richer with time. As the tidal tails of stars and gas stretched across space, their radio telescopes would detect the faint, characteristic radio whisper of neutral hydrogen gas, the raw material of stars being pulled and stretched into these vast structures. The most patient observers, those who watched for billions of years, might even be fortunate enough to capture the finale. In the last few minutes before the two supermassive black holes merged, their instruments could, in theory, detect the crescendo of gravitational waves, ripples in spacetime itself, emanating from our corner of the universe. This would be the ultimate confirmation of the merger's completion, a signal that two galactic hearts had become one. This is not speculative fiction. It is exactly how we study the universe right now. When astronomers point the Hubble Space Telescope at the Antennae galaxies or the James Webb Space Telescope at a chaotic merger in the early universe, they are those distant observers. They see the brilliant knots of starbursts, measure the infrared glow of dust, and map the radio waves from streaming gas. They are piecing together the life story of galaxies they will never visit, understanding that these spectacular collisions are not rare disasters, but essential chapters in galactic evolution. Our impending fate with Andromeda is simply one more example of this universal process, playing out in slow motion right next door. It is a humbling shift in perspective, realizing that our own galactic identity crisis will one day be just another entry in a catalogue of cosmic transformations, a single point of light telling a familiar, beautiful, and violent story to anyone who knows how to look. Our galactic story has a third character, a smaller sibling caught in the same gravitational web. The Triangulum galaxy, also known as Messier 33, is the third largest member of our local group. While Andromeda and the Milky Way are the dominant giants, Triangulum is a more modest spiral, holding perhaps only a tenth of the stars of our own galaxy. For eons, it has orbited the immense Andromeda, a satellite caught in its larger companion's powerful gravitational field. But as the great merger unfolds, Triangulum's fate becomes an intriguing subplot, a variable that adds fascinating complexity to our cosmic forecast. Current observations suggest it is on its own trajectory, one that may bring it into close contact with the merging giants. The key uncertainty for astronomers is not if it will be affected, but how. Will it be swept up in the chaos, becoming a direct participant? Recent supercomputer simulations, which model the gravitational dance of all three galaxies, present several compelling scenarios. In one possible future, Triangulum's current path leads it on a dramatic course toward our own Milky Way. It could, in fact, strike our galaxy before Andromeda even arrives, a preliminary sideswipe that would further disrupt our spiral structure and add its own stars to the coming mix. Other simulations suggest a different destiny, where it remains more tightly bound to Andromeda, merging with it first before the combined entity then collides with the Milky Way. There is also a chance it could avoid a direct merger altogether, instead being gravitationally slung into a wide, eternal orbit around the new Milkdromeda, becoming a permanent satellite galaxy. Each of these paths is possible because the exact measurement of Triangulum's sideways motion, just like with Andromeda a century ago, still holds a degree of uncertainty. This small galaxy's inclusion transforms our models from a simple two-body problem into a dynamic three-body puzzle. Its gravity, while smaller, can nudge the trajectories of the larger players in subtle ways, potentially altering the precise timing and angle of the main collision. In some simulations, this interaction even leads to a spectacular, though unlikely, triple merger, where all three galaxies become entangled simultaneously. This subplot underscores a profound truth about our cosmic neighborhood. It is not a static collection of isolated islands, but a dynamic, interacting family. The fate of each member is inextricably linked to the others through gravity's invisible threads. As we watch the slow-motion ballet of the Milky Way and Andromeda, we must also keep an eye on their smaller sibling, a reminder that even in the vastness of space, no galaxy is an island. These galactic fates are not prophecies, but predictions born from digital universes. The challenge of forecasting such an event is almost incomprehensible, involving tracking the gravitational dance of hundreds of billions of stars, trillions of suns worth of dark matter, and swirling oceans of gas across billions of years. To solve this, astronomers don't use telescopes, they use supercomputers. They build synthetic cosmos inside machines, creating the most sophisticated video game of all time, where the only objective is to reveal destiny. Projects with names like IllustrisTNG or the Via Lactea simulation are the virtual laboratories where our future is tested. These are not simple animations, they are complex physical models that simulate different cosmic ingredients. Dark matter particles provide the gravitational scaffolding. Clouds of virtual gas can collapse to form stars. Supermassive black holes grow and release energy. The physics governing these digital universes is coded from the same laws that govern our own. One of the foundational techniques is called the n-body calculation. It sounds technical, but the concept is straightforward. Every single star, or more often, every clump of material representing many stars, is treated as a single point, a body, with its own mass and velocity. The computer's monumental task is to calculate how every single one of these n-bodies gravitationally influences every other one, for every tiny step forward in time. For just two bodies like Earth and the Sun, this is simple math. For three bodies, it becomes famously chaotic. For hundreds of billions, it requires some of the most powerful supercomputers on the planet, running for months. To handle the behavior of gas, scientists use a method called smoothed particle hydrodynamics. Here, a fluid like interstellar gas is modeled not as a continuous sheet, but as a collection of discrete particles that flow and interact with each other, allowing the simulation to capture how gas shocks, cools, and forms stars during the violent merger. As one computational astrophysicist might explain, the art is in the balance, choosing the right resolution to capture the large-scale story without getting lost in the microscopic details of every single star. The process begins with our best current snapshot of the universe, the observed positions, masses, and velocities of the Milky Way and Andromeda. The simulation is set in motion, and the laws of physics take over. But how do we know we can trust what the computer shows us? This is where validation is key. Scientists test their virtual universes by asking them to recreate things we can already see, like the present-day shapes of galaxies or the large-scale cosmic web. If a simulation can accurately reproduce the known universe, it gains credibility for forecasting the unknown. These digital experiments are then run thousands of times with slight variations in initial conditions, creating a statistical forecast of probable outcomes. It is through this relentless digital experimentation that we see our solar system's likely path to the galactic halo, witness the brilliant starbursts, and watch the black holes merge. They transform the silent, patient future into a vivid, visual story, giving us a front-row seat to the greatest show our local universe will ever stage. The collision's timeline stretches far beyond any monument, dynasty, or even the lifespan of our species. Why should an event set for a future so distant it defies meaning matter to us today? The answer lies not in the event itself, but in the light it casts backward through time, illuminating our present understanding of the cosmos. This grand future merger is a master key, unlocking mysteries about our universe's past and its fundamental workings right now. By studying where we are ultimately headed, we learn how we got here. The violent dance between the Milky Way and Andromeda serves as a nearby laboratory, a controlled experiment written across the sky. When astrophysicists create their supercomputer simulations to forecast this merger, they are not just predicting the future, they are testing the very laws of physics that govern all galaxies. The behavior of the dark matter halos, the triggering of starbursts, the final coalescence into an elliptical shape, each of these predicted phases is a check on our models of cosmic evolution. If our simulations can accurately foretell the fate of these two familiar giants, it gives us tremendous confidence that we understand the processes that shape the strange, distorted galaxies we see in the deep universe. This distant future is a mirror reflecting the truth of our present science. Our drive to map this event fuels technological innovation in the here and now. Measuring the sideways motion of Andromeda required the Hubble Space Telescope to perform feats of precision at the absolute limit of its engineering. Future missions designed to study even fainter objects or detect the gravitational waves from merging black holes are propelled by the desire to confirm these grand cosmic narratives. The quest to understand a future we will never see directly advances the tools we use to explore everything else. On a deeper level, this knowledge reshapes our philosophical place in the universe. For millennia, humans have looked up at the Milky Way and seen permanence, a stable home etched into the heavens. We now know that even this majestic structure is transient, a single beautiful frame in a long cosmic film. This can be a humbling realization, but also a liberating one. It connects our story to a grander narrative of transformation and renewal that operates on scales we can barely comprehend. Our desire to understand this fate, to trace the arc of our galactic story from birth to merger, speaks to a profound curiosity that defines us. We are the part of the universe that has awakened to contemplate its own origins and its ultimate end. So while we will not witness the tidal tales or the new black hole, by unraveling this future we come to know our home and our moment in cosmic history with a little more clarity, weaving our brief, brilliant human timeline into the vast, patient tapestry of galactic time. The word violent can be misleading. It suggests a sudden, fiery cataclysm, a cosmic car crash where stars explode on impact. But the reality of a galactic merger is far stranger and more profound. The violence is not one of fire and shrapnel, but of gravity and time. It is a slow-motion rearrangement on a scale so vast our minds struggle to frame it. To understand this, we must first confront the most persistent myth, the idea of density. A galaxy seems packed with stars, but that is an illusion of distance. If you reduce the Milky Way to the size of a dinner plate, its stars would be finer than grains of sand, separated by miles of empty space. Even in the crowded core, stars are typically light weeks or light months apart. So when we say two galaxies collide, we are not describing a bumper car arena. We are describing two vast, mostly empty clouds passing through each other, their individual stars so far apart that direct collisions are almost unthinkably rare. The true violence happens to the architecture of the galaxies themselves, not to their stellar inhabitants. It is the gravitational tides, those immense, invisible hands, that do the destructive work, stretching and shredding the grand designs over epochs. This leads to a second crucial clarification about timescale. A galactic merger is not an event you could watch in a lifetime, or even across the entire history of human civilization. It is a process that unfolds over billions of years. The word collision implies a moment of impact, but for galaxies, the first close pass is merely the beginning of a billion-year-long dance. The spectacular tidal tails and starbursts are not a brief flash. but a phase that persists for hundreds of millions of years. An astronomer studying such events would remind us that from a cosmic perspective, this is a stately, inevitable transformation, not a sudden disaster. This directly debunks the most human-centric fear, the certainty of our solar system's destruction. As we explored earlier, while our place in the galaxy will change dramatically, the physical integrity of our sun and planets is overwhelmingly likely to remain. We are not passengers in a doomed ship, but rather in a vessel being gently, if chaotically, towed to a new harbor. The violence of the merger is real, but it is a structural violence, a reshaping of the cosmic landscape on a grand scale. It is the violence of a continent drifting, not of a bomb exploding. Setting this record straight is essential, not to diminish the spectacle, but to appreciate its true nature. It moves us from a vision of apocalyptic fire to an understanding of a majestic gravitational symphony, where the music is written in billions of years and the instruments are entire galaxies. The future of our galaxy is not a mystery. It is already written in the light of other merging systems scattered across the cosmos. To understand our own fate, we look to celestial laboratories, galaxies caught in the act of collision right now. Among the most telling are the Antennae galaxies, two spirals whose long, streaming tails of stars and gas resemble an insect's antennae. This is exactly what supercomputer simulations predict for the first close pass between the Milky Way and Andromeda, a preview happening 50 million light-years away. Another remarkable example is NGC 6052, which appears in telescope images as a chaotic, glowing blob. But this is not a single, misshapen galaxy. It is two separate disk galaxies caught in the process of merging, their once distinct structures now violently intertwined into a single, turbulent mass of light. Observational astronomers use instruments like the Hubble and James Webb Space Telescopes to dissect the light from these systems, transforming them from pretty pictures into data-rich forecasts. Hubble's sharp vision reveals the intricate details of the tidal tails and the brilliant blue knots of superstar clusters, each knot containing millions of newborn suns. The James Webb Space Telescope, with its infrared eyes, peers through the obscuring dust to see the raw material of the merger, mapping the heated gas and pinpointing the sites of hidden star formation that optical telescopes cannot see. These observations provide an empirical checklist for the phases of a major merger. We see the gravitational tides pulling the galaxies apart. We confirm the intense compression of gas clouds that triggers firestorms of new stars. We measure how the once orderly rotation of the spiral disks is scrambled into chaos. The key practice for astronomers is to use these systems as direct analogies, comparing their current observed state to specific moments in the simulated timeline of our own galactic future. There are, of course, differences. The Milky Way and Andromeda are both more massive than the galaxies in the Antennae, which means our merger will create an even larger final elliptical galaxy. The angle of our collision and the presence of the Triangulum galaxy add unique complexities, but the core physics remains identical. The violent relaxation that turns spirals into ellipses, the ignition of starbursts from shocked gas, the eventual quieting of the new galaxy, these are universal processes. By studying these distant, ongoing collisions, we are not just looking at alien galaxies, we are watching home movies of our own future, played back at high speed from a great distance. They provide the crucial evidence that our models are not just elegant simulations, but accurate reflections of a story that has already been told countless times throughout the universe. Deep in the heart of the new galaxy, the final act is about to begin. Two unfathomably dense points of pure gravity, the merged cores of the Milky Way and Andromeda, now orbit one another in a closing spiral of ultimate consequence. Each is a supermassive black hole, one containing the mass of over 4 million suns, the other over 100 million. Their dance is silent and dark, visible only through its effect on the stars unfortunate enough to wander near, their paths whipped into impossible trajectories by the warped spacetime around these monsters. As they draw closer, their orbital speed increases from a stately cosmic waltz to a frenzied, relativistic whirl. In the last few years before merger, they will complete thousands of orbits every single second, moving at a significant fraction of the speed of light. This is the Inspiral, the final death spiral of two titans destined to become one. The energy involved is beyond human scale, a significant fraction of the total mass of our Sun converted into pure, rippling energy that will flood the local universe. But this energy does not emerge as light or heat in any traditional sense. It radiates outward as something far more fundamental, a vibration in the fabric of reality itself. These are gravitational waves, the most profound prediction of Einstein's theory of general relativity. Picture spacetime not as a static stage, but as a flexible, invisible fabric. When massive objects accelerate like these whirling black holes, they create ripples in that fabric, much like a spinning dumbbell churns the surface of a pond. These ripples propagate outward at the speed of light, stretching and compressing everything in their path, an alternating squeeze and stretch of space itself. For the final moments of the black hole merger, the entire local group of galaxies will be immersed in this silent, rhythmic distortion. Detecting such a signal from our own future merger is, of course, impossible for us, but it is a primary target for the astronomers of the far future, or for any advanced civilization within millions of light years equipped with the right technology. That technology is already in development today. Missions like the European Space Agency's Laser Interferometer Space Antenna, known as LISA, are designed to listen for these cosmic ripples. LISA will not be a single telescope, but a constellation of 3 spacecraft, flying in a perfect triangle millions of kilometers apart, connected by lasers. As a gravitational wave passes through, it will minutely change the distance between the spacecraft, a distortion smaller than the width of an atom. By monitoring these laser links with phenomenal precision, LISA will act as a galactic microphone, tuning into the low-frequency hum of merging supermassive black holes across the universe. A scientist working on the LISA project might describe their goal as charting the gravitational wave background of the cosmos, a symphony of collisions that underpins galactic evolution. The signal from the Milkdromeda black holes would be a unique note in that symphony. It would be an extremely low-frequency wave with a single cycle taking months or even years to complete, corresponding directly to the final, slow inspiral of the black holes. Its amplitude or strength would be monumental, a direct testament to the incredible masses involved. Detecting it would provide a perfect, clean confirmation of the merger's completion, a timestamp for the birth of the new galactic core. More than that, the precise shape of the gravitational wave signal would tell future scientists everything about the event, the masses and spins of the original black holes, the orientation of their orbit, and the properties of the resulting single black hole. It would be a data-rich broadcast from the heart of the collision, a final, definitive signature that the long galactic dance was over, and a new, quiet era had begun. The final gravitational waves have long since faded into the cosmic background. Milkdromeda now exists as a single, unified entity, a vast island universe entering an era of profound quiet. Billions of years after the last stars were flung into chaotic orbits and the central black holes merged, the galaxy has settled into a new, permanent form. It is no longer a place of dramatic change, but one of deep cosmic stability. The brilliant blue fire of starbursts has been extinguished for eons, leaving behind the cooler, steady glow of ancient suns. This is the signature of a giant elliptical galaxy, often described by astronomers with a simple, evocative phrase, red and dead. Its light is not the mixed palette of a spiral with its vibrant blue star-forming regions, but a uniform reddish hue. This color tells the story of its stellar population, dominated by older, longer-lived stars that burn at lower temperatures. The massive, short-lived blue stars that once lit up the merger have all ended their lives in supernova, their ashes scattered. What remains is a galaxy of pensioners, stars quietly burning through the final stages of their long lives. The structure itself is a study in smooth simplicity. Gone are the elegant spiral arms, the distinct lanes of dust, the flat, rotating disk. In their place is a three-dimensional swarm, a shape resembling a glowing football or a diffuse cloud of light. From any angle, it presents the same smooth, featureless profile because its stars are not moving in an orderly rotation. They buzz around in every direction, like a hive of bees with no central flight plan, their orbits randomized by the violent relaxation of the merger. This lack of a preferred direction is what gives the elliptical its rounded, often slightly elongated form. Another defining characteristic is its atmosphere. Enveloping the entire stellar swarm is a massive halo of extremely hot, thin gas. This gas is not the cold, star-forming fuel of a spiral galaxy. It is superheated to millions of degrees, likely by the combined energy of all those ancient supernova and the final outbursts from the merging black holes. It glows faintly in X-rays, an invisible shroud that prevents any remaining cooler gas from collapsing to birth new stars. This is the state of quenching, where a galaxy's star-forming engine has been permanently shut off. The path to this red and dead state was sealed during the merger itself. The processes that made the collision so spectacular also ensured its future tranquility. First, the galaxy exhausted its fuel. The same intense starburst that created those brilliant blue clusters consumed the vast majority of the available cold hydrogen gas at a ferocious rate, using it up in a final, glorious burst of creation. Second, what little gas remained was either heated into the hot halo or blown entirely out of the galaxy by powerful winds from supernova and the active galactic nuclei. Without a steady reservoir of cool, dense gas, the galaxy cannot form new stars. The existing stellar population simply grows older together, collectively reddening over time. This is the ultimate fate of most massive galaxies in dense environments, a natural progression in cosmic evolution. Our local group, once home to two vibrant spirals, will have matured into a single, serene elliptical. From within this quiet galaxy, the night sky for any surviving worlds would be profoundly different. The sky would be darker, with stars more evenly scattered in all directions, lacking the dense, luminous band of a Milky Way. The constellations would be fixed for billions of years as stellar motions become almost imperceptibly slow. New celestial wonders, like glowing nebulae or brilliant young star clusters, would be relics of an impossibly distant past. This raises a reflective question for the far future. What would drive the curiosity of beings in such a stable, ancient galaxy? When the primary drama of galactic evolution is over, and the universe continues its expansion, cooling and darkening, where does the spirit of exploration turn? Perhaps inward, to the intricate physics of planets and stars, or outward, to the deepening mystery of the space between galaxies. The story of Milkdromeda reminds us that cosmic history has chapters of fiery transformation and eons of quiet aftermath, and our galactic home is destined to experience both. Yet even as Milkdromeda settles into its final form, a far grander and more relentless process continues in the darkness beyond. The universe itself is expanding, carrying the distant families of galaxies away from our own local group at ever-increasing speeds. This expansion is not a gentle drift, it is an acceleration, a fundamental feature of space itself stretching over time. While the gravity within our local group is strong enough to hold the Milky Way, Andromeda, and their satellite galaxies together, the gravitational glue between different galaxy clusters is not. They are being pulled apart by the expansion of the universe itself. Cosmologists describe a future where this expansion becomes the dominant story. Over hundreds of billions of years, every galaxy cluster outside our own will recede so far and so fast that their light can no longer reach us. They will cross a cosmic horizon and vanish from view one by one. The brilliant tapestry of the extragalactic universe, the very map that allows us to understand our place within it, will fade to black. Our local group, having merged into the single entity of Milkdromeda, will become an island universe in the most literal sense, a solitary island of stars adrift in an ever-growing, ever-darkening void. Physicist Lawrence Krauss has contemplated this profound isolation, noting that for any civilization in that far future, the universe will appear profoundly lonely. All evidence of the Big Bang, of an expanding cosmos filled with billions of other galaxies, will be lost to them. Their sky will contain only the stars of Milkdromeda. They will have no way of knowing a vaster, richer universe ever existed beyond their own galactic borders. This places our impending merger into the ultimate cosmic context. The violent collision and beautiful rebirth of Milkdromeda is not the final chapter, but merely a middle act in a much longer story of cosmic evolution. It is the process by which our local neighborhood consolidates itself before the long night of isolation falls. For us today, this knowledge is a gift of timing. We live in a privileged cosmic era, a narrow window where the universe is still transparent enough to see its own structure, yet old enough for galaxies to have formed and evolved. We can witness other mergers, measure the expansion, and piece together the universe's history and fate. A far future astronomer born in Milkdromeda would see a static, self-contained universe with no clues to its dynamic past. Their cosmology would be built on a single data point, their own galaxy. This shifts our perspective on the merger from a local catastrophe to a necessary consolidation, a gathering of resources and stars before the long, quiet journey into a profoundly lonely future. It asks us to consider what we would believe if we saw only one galaxy in an otherwise empty sky, and how fortunate we are to live in an age when the cosmos still shows us its grandest secrets. Their cosmology would be a puzzle with only one piece, their own galaxy. But even a solitary giant like Milkdromeda holds whispers of its violent birth, secrets buried in the motions and chemistry of its ancient stars. A future civilization, rising long after the merger's final echoes have faded, would become cosmic detectives, practicing a science we might call galactic archaeology. Their task is not to predict the future, but to excavate a past they never witnessed, piecing together the biography of their home from the stellar fossils that remain. The first clue might be found in the galaxy's outer halo, in faint, ghostly rivers of stars. These are the last remnants of the majestic tidal tails, streams of stars pulled from the Milky Way and Andromeda during their first dramatic pass. Billions of years later, these streams would have diffused, their stars slowly mixing into the general halo, but their subtle, coherent motion might still be detectable. Advanced surveys could reveal groups of stars moving together on similar, unusual orbits, a telltale sign they were once part of a structure that was torn apart. These stellar streams are the galactic equivalent of finding pottery shards from two distinct ancient cultures scattered across a single archaeological site, hinting at a convergence. Deeper within the galaxy, the globular clusters would tell another chapter of the story. These are dense, spherical swarms of hundreds of thousands of ancient stars, some nearly as old as the universe itself. In a pre-merger galaxy, these clusters orbit like loyal satellites. The violent merger would have stripped many from their original galaxies and redistributed them throughout Milkdromeda. A future astronomer cataloging these clusters would discover distinct families. One family might orbit in a certain plane, bearing the chemical signature, the specific heavy element mix, characteristic of the Milky Way's original population. Another family on wildly different orbits might show the unique chemical fingerprint of stars born in Andromeda. Finding these two distinct populations intermingled in a single galaxy would be powerful evidence that two separate star-forming systems once existed and later combined. The most definitive evidence would lie at the very heart of the galaxy. Measurements of stars orbiting the central supermassive black hole would reveal an object of staggering mass, perhaps 150 million times that of the Sun. Such a behemoth is too large to have grown quietly from a single seed. Its existence strongly suggests a major merger, an event where two large black holes coalesced, their masses adding together. Careful study might even detect a slight wobble in the orbits of the innermost stars, a possible relic of the black hole receiving a powerful kick from the gravitational waves emitted during that final merger, a cosmic recoil that took eons to settle. Yet time is the great eraser. Many clues would fade. The brilliant blue star clusters from the Starburst era would have burned out and dispersed eons ago, their constituent stars lost in the crowd. The specific, chaotic orbits from the merger's peak would have been smoothed by gravitational interactions over billions of years, a process called phase mixing. The hot X-ray emitting gas halo, while evidence of a violent past, would not directly point to two spirals. The challenge for our future detectives is immense. They would need to separate the signal of the Great Merger from the noise of billions of years of subsequent stellar evolution and smaller galactic acquisitions. This thought experiment does more than forecast a distant science. It reflects our own current struggle. We are those galactic archaeologists right now, looking at other elliptical galaxies in the distant universe, using the same techniques to deduce that they too are the products of ancient mergers. Our impending fate with Andromeda provides the key to interpreting those far-off fossils. It teaches us that even the most cataclysmic events leave only subtle, encoded signatures across cosmic time, a history written not in stone, but in the slow dance of stars and the silent memory of elemental chemistry. That famous image of Earth as a pale blue dot suspended in a sunbeam already shrinks our world to a fragile speck. Now place that dot within our story, a speck not just in a quiet spiral, but in a merging galaxy destined for collision. Our planet becomes a pale blue dot in a pinball machine of stars, a mote of dust caught in a gravitational storm that will rage for billions of years. This cosmic perspective does more than humble us. It reframes the very scale of our concerns. All of recorded human history, every empire, every invention, every triumph and tragedy, occupies less than a blink in the timeline of this galactic merger. Our greatest ambitions and deepest conflicts unfold on a stage that is, from this vantage point, unimaginably small and temporary. What legacy can we possibly build when the galaxy itself is not forever? The knowledge can feel overwhelming, as if our brief moment of consciousness is utterly insignificant against the cosmic clock. But there is another way to see it. This vast backdrop does not erase meaning, it redefines it. The fact that we are here at all on this tiny world, with minds capable of tracing the arc of stars across billions of years, is itself a staggering wonder. We are the universe become conscious, looking out at its own unfolding story. In a cosmos where galaxies merge and stars are born and die, the rarest thing we know of is not the collision of titans, but the spark of awareness that can comprehend it. Our fleeting moment is not a footnote, it is the page where the universe reads its own history. So what matters in the face of such deep time? Perhaps it is the quality of our observation, the depth of our curiosity, and the connections we forge in our brief shared light. The merger of the Milky Way and Andromeda, a fact of astrophysics, becomes a mirror. It shows us that permanence is an illusion at every scale, from our lives to our galaxies, and in doing so, It asks us to value the transient, beautiful now we are given to explore, to understand, and to simply be. This cosmic story begins with a faint shift of blue light and ends in a silent red glow. From the first clue in a spectrograph to the final elliptical giant, we have traced the arc of our galaxy's most profound transformation. The ultimate lesson here is not one of dread for a chaotic future, but of profound awe for a universe in motion. Our home in the stars has a biography, a dynamic history of growth and interaction, and a destiny already shaped by the fundamental forces that weave the cosmos together. This knowledge places us in a remarkable position. We are temporary residents of a temporary spiral arm, yet we possess the extraordinary capacity to map this grand sequence across billions of years. We can run the simulations, decode the light from other mergers, and forecast the quiet fate of Milkdromeda. This ability to look backward and forward across cosmic time is perhaps our most meaningful connection to the universe itself. It transforms the night sky from a static painting into a living narrative. So the next time you find yourself beneath a clear, dark sky, look toward that faint smudge of Andromeda. See it not as a distant curiosity, but as a partner in a slow, graceful dance that will one day reshape our entire celestial home. Let that understanding fill you with wonder, for the stars above are a testament to an endless story of change, and we are here for a fleeting moment to read its pages. If this journey through cosmic destiny reshaped how you see our galaxy, share your perspective with others who look up in wonder. Your thoughts and questions are always welcome, and subscribing ensures you never miss our next exploration into the deepest mysteries of space.